So here's a more detailed look at an initial rate law experiment where you actually have to determine the rate law with the values of the exponents and k based on a series of experiments. We have hydrogen peroxide reacting with iodine in the presence of 2 moles of an acid catalyst to produce the triiodide ion and 2 moles of water. In the data that we're going to look at, we're going to see 4 experiments where the concentrations of the iodine were determined by manipulating the concentrations of the hydrogen peroxide, the iodide, and the catalyst. And we want to calculate out what the exponents are for each of the reactants and catalysts, and we also want to calculate out what the value of the rate constant is. So let's take a look at the data. So here are our 3 experiments. In experiment 1, we have the concentration of the hydrogen peroxide to be 0.01 molar, iodine to be 0.01 molar, and the hydrogen ion concentration to be 5 times 10 to the negative 4 molar. In experiment 2, what concentration have we doubled? The hydrogen peroxide concentration has been doubled, and we kept the iodine concentration the same, 0.01 molar, and the hydrogen ion concentration is the same. In this case, we can now compare experiment 1 to experiment 2, because you have to, if you have more than one variable, you have to keep the other variables constant and only double one. Otherwise, it won't work properly. So I'm going to compare experiment 2 by dividing experiment 2 by experiment 1. Okay? So in this case, the rate for experiment 2, will be 2.3 times 10 to the negative 6. We're going to divide that by 1.15 times 10 to the negative 6. That's going to be equal to k sub 2 divided by k sub 1. Now for the second experiment, what's going to happen to the concentration of the iodide and the concentrations of the hydrogen ions in terms of the math? They're going to cancel, right? They have to cancel. So what we're going to be left with on the right-hand side of the equation is the concentration of the hydrogen peroxide, the 0.02 molar, divide that by the concentration of the hydrogen peroxide in the first experiment, all raised to the nth power. At this point, we can now solve for n. The k's are going to cancel because they're constants. So 2.3 divided by 1.15 is going to give us a 2 on the left-hand side. That's going to be equal to 0.02 divided by 0.01 raised to the n power, 2 to the n. And when you have 2 to the n must equal 1. So our first exponent for the hydrogen peroxide is 1. N equals 1. Questions on that one? All right, so now looking at the data, what other experiments can I possibly compare? Let's take a look at the iodine. If we look at experiment 3, relative to what? Not experiment 1. You can't compare experiment 3 and experiment 2. Why? For the iodine.
They're not constant.
They're not constant. You have to keep them constant because if you look at it,
You do either 1 or 2 or 2 and 4.
yeah,
4 and 1.
we can do basically we can do experiment 4 to experiment 3. So here's one where we aren't going to do 2 and 1. Who asked that question? Yeah. If you look at this one, if you use experiment 4 as your baseline, we are keeping the hydrogen peroxide relative to experiment 3 constant. We are doubling the concentration of the iodide from experiment 4 to experiment 3 as 0.02. So 0.01 goes to 0.02. But what's happening here? Can we do experiment 4? No. All right. What about experiment 1 directly to experiment 3. If we do experiment 1 to experiment 3, hydrogen peroxide is still 0.01 molar. Iodide is being doubled. And the hydrogen ion is being kept constant. So we can use experiment 3 relative to 1. So experiment 3, what's going to happen to the concentration of the hydrogen ion and the concentration of the hydrogen peroxide in terms of the math? They're going to cancel, correct? So they basically cancel out. So the only thing we have to worry about in this case is the iodide. So our rate in experiment 3 is going to be 2.3 times 10 to the negative 6. That's going to be divided by the rate in experiment 1, 1.15 times 10 to the negative 6. And that's going to equal K sub 3 divided by K sub 1. And we're going to multiply that by the concentration of the iodide in experiment 3, which is 0.02. Divide that by the concentration of the iodide in experiment 1, which is 0.01, both raised to the m power. What happens to K3 and K1 in this example? They cancel out. On the left-hand side, 2.3 divided by 1.15 is going to be 2. So I get 2 is equal to 0.02 divided by 0.01 obviously gives me 2 raised to the m power, and m happens to be 1. So it's 1 also for our exponent on the iodide. Questions on that one? So we have one more to do. Now we have to look at the hydrogen ion concentration. So we have to be able to double our hydrogen peroxide, or excuse me, double our hydrogen ion concentration and keep everything else the same. And it looks like we're going to do experiment 1 relative to experiment 4. Because if you look at the hydrogen peroxide and the iodide, they're both 0.01 molar in experiment 1. And experiment 4, they're both 0.01 molar. So in our mathematical expression, they're going to end up canceling. And if we go from the hydrogen ion in experiment 1 to the hydrogen ion in experiment 4, what happens? It doubles. So taking a look at this experiment, the rate in experiment 4 is 1.15 times 10 to the negative 6. And we're going to divide that by the rate in experiment 1, which is also 1.15 times 10 to the negative 6. That's going to be equal to K sub 4 divided by K sub 1. We're going to multiply that by the concentration of the hydrogen peroxide in experiment 4. It's 0.001 molar. Divide that by what it is in experiment 5, or excuse me, experiment 1, 0.0005 molar. And this is all raised to the p power. On the left-hand side of the equation, what happens to the rate? It becomes 1. The k's are going to cancel. And 0.001 divided by 5 times 10 to the negative 4 is 2 raised to the p power. And solving for p, we get p equals 0. So the exponent for the hydrogen ion is 0. It's 0 order with respect to the hydrogen ion, first order with respect to the hydrogen peroxide, and first order with respect to the iodide. What's the last thing we want to do here? We now want to write our rate law out. So our rate is going to be equal to K times the concentration of the hydrogen peroxide raised to the first power times the concentration of the iodide raised to the first power and times the concentration of the hydrogen ions raised to the 0 power. And that's basically going to do what? that's just going to be 1 at that point. And if we plug in some data here, I'll plug in experiment 4. You could plug in experiment 1, it doesn't matter, but since I can see experiment 4, I'm just going to plug that one in. So plugging in the rate, 1.15 times 10 to the negative 6, that's going to equal K times the concentration, 0.01 to the first power, times the concentration of 0.01 to the first power. That hydrogen ion concentration is just going to be a 1. Divide both sides by 0.01. That's going to cancel. So dividing this side by 0.01 squared. 1.15 exponential negative 6. Divide that by 0.01 squared. I get 0.0115. And what are the units for K going to be? Just going through here and looking at the units. In the numerator, we're going to have molarity over seconds. In the denominator, we're going to have molarity squared, right? Looking at our complex fraction, it's going to be 1 over molarity squared. So we're going to get reciprocal molarity, reciprocal seconds as our units for K. That's the value of K. So ultimately, what does our rate law look like? Our rate equals 0.0115 reciprocal molarity, reciprocal seconds, times the concentration of hydrogen peroxide raised to the first power times the concentration of the iodide raised to the first power times the concentration of the hydrogen ion raised to the 0 power. That's the rate law for that experiment.